Hello again. Today we're going to be talking more about the derivative. In the last video, we talked about the derivative of a function at a value x equals a. So we were thinking of it as being at a fixed value a. But today I want to talk about the derivative as a function of x, rather than thinking of the derivative at a specific constant value. We're going to think about the derivative of a function everywhere. So this is our definition of the derivative of a function at x equals a. And all we're going to do is replace the a with x's instead. And now we can talk about the derivative of the function at any value of x. Okay? So this is going to be our definition of the derivative of a function at any value x. So I'm going to use this definition, do a quick example. So let's say we're given the function f of x equals x squared plus x, and I want to find the derivative using the definition. Okay, so the derivative with respect to x is the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay. So first, what is f of x plus h? So it's going to be our function, but we're going to be plugging in the value x plus h into our function for all of the x's. So this x is going to get replaced with x plus h, and that x is going to get replaced with x plus h. And we're going to have to remember to square that. So it's going to be x plus h in parentheses squared plus x plus h. By the way, one good way to do this, especially when it comes to functions that have x's in multiple places, see there's two x's, is maybe you might want to write down the pattern, leaving a blank parentheses for each one of your x's, then fill in the blank parentheses with the expression x plus h. So just a little tip. Okay. Next, we want to subtract f of x. F of x is simply this function right there. But we need to remember to subtract the whole thing. So I'm going to put that in a parentheses, and I'll distribute the minus sign in the next step. Okay. Now, by the way, you can't just jump the gun and try to plug in h equals 0. It'll turn out that it'll be 0 over 0, which is indeterminate, which means you need to simplify. So we need to simplify this. Squaring that term gives us x squared plus 2xh plus h squared. And the 2xh comes from the product of the inner and the outer, if you were to write it twice and FOIL it. Okay, and then plus x plus h minus x squared minus x. Okay, we got some terms that can cancel. We can cancel out an x squared. We can also cancel out this plus x and this minus x. So that leaves us with 2xh plus h squared plus h all over h. Well, every single term in the top has an h in it, so we can just divide by h everywhere. So dividing by h on the top and bottom leaves us with 2x plus h plus 1. And then the limit is h approaches 0. Just plug in 0 for h and you get 2x plus 1. So the derivative of the expression x squared plus x is the equation 2x plus 1. Okay. Some other topics related to derivatives is there are more than one way to write or denote the derivative of a function. For this particular function, we found the derivative was 2x plus 1. Another way you can write that is you could put d dx of f of x. So this means you're taking the derivative with respect to x of your function f of x. In later chapters, see the prime, you don't need to denote that it's a derivative with respect to x. It's just assumed to be a derivative with respect to your independent variable. Here, it's just making it explicit that we're taking the derivative with respect to x. And maybe in later chapters, we might be dealing with functions of more than one variable like x and y. Then it'll become important to denote what derivative you're talking about, the derivative with respect to x or the derivative with respect to y. And then the prime notation just won't work in that case because it's not specific enough. So that's one reason why this notation is used. It's called Leibniz notation. It's a little bit more specific when you need it, essentially. Okay, a couple of other ways that, oh, and by the way, this is the same thing as the derivative, so it's still 2x plus 1. Another way you can write a derivative is, what if our function was just not written as f of x equals, but just y equals x squared plus x? Then you can say that y prime is 2x plus 1. It's the same prime notation, just put it above your y like that. And of course, that is the same as dy dx. And this is really the same notation as this. It's just the y doesn't need to be put in parentheses beside it like that. You can just put the y on top and write it as dy dx. Okay. Some other small notes. If you're talking about higher derivatives, like a second derivative, third derivative, fourth derivative, a second derivative is just taking the derivative of your function once, and then taking the derivative of that, and that gives you the second derivative. Okay, so you would denote the second derivative of f of x as f double prime x. That's the second derivative. Third derivative, put 3 little primes. Past the third derivative, they start using a number in parentheses. So this doesn't stand for fourth power, it's the fourth derivative of your function. Okay? If you were using Leibniz notation, the second derivative of a function is written like this: d squared over dx squared of f of x. Or if you just call f of x y, you would write it like that: d squared y over dx squared. Yeah, the reason for this sort of notation is this is the first derivative, dy dx, and then if you're taking the derivative with respect to x of that, you'd write it this way. So then to compress it, the two d's, think of them as just combining together and writing d squared. So that's why only the d is squared and not the y. And then in the bottom you have a dx and another dx. And so if you put those two together, you can think of that as dx squared. Now normally they don't put the parentheses, but it's just understood that this whole dx is being squared, not just the x. Okay, anyway, that's just a different notation. You should get used to it as you see it over and over again in your problems in your textbooks. Okay. Let's now talk about when a derivative is undefined and when it's defined or undefined. So there are going to be 3 cases where the derivative is not going to exist. Okay. Case 1 is if f of x is not continuous at x equals a, then the derivative doesn't exist at x equals a. Okay, so the function has to be continuous to even possibly have a derivative. Okay, but if it's not continuous, it definitely doesn't have a derivative. Okay, so lack of continuity is one way that a derivative cannot exist. The other is what I call a sharp turn. An example of this would be the equation y equals absolute value of x. That's the absolute value function. It has a sharp turn at x equals 0, therefore the derivative does not exist at x equals 0. This is because the slopes from the left side would make you think the slope is -1, but slopes, if you look at the right side of 0, makes you think it's +1, and therefore the limit from the left and the limit from the right aren't going to be the same value, so the limit doesn't exist. The derivative is a limit equation, and that's why. Sharp turns cause the limit from the left and the right to not be the same value. Okay, and the third way a function, the derivative doesn't exist, is if the function has a vertical tangent line. Okay, an example of this would be y equals x to the 1/3 power, which looks like this. And you see, once again, at x equals 0, that's the problem here, is that it's temporarily making a vertical tangent line. It's temporarily going straight up for just a second at x equals 0. And just from geometry or the definition of the slope, slope is supposed to be rise over run. And if you have a vertical line, 2 points on a vertical line, the run would be 0. There's no change in x coordinates. Okay, so those are the three ways on a graph that the derivative is going to fail to exist. Is if we have a discontinuity, we have a sharp turn, or we have a vertical asymptote. Also, conversely, if you happen to know the derivative does exist, that must mean it is a continuous function at that point, that there isn't a sharp turn, and that it's not a vertical tangent line. Now, out of that statement, probably the most important is the fact that if the derivative exists, then it must be continuous. So that's sort of the reverse of this statement, that if it's not continuous, it's not differentiable. So if it is differentiable, it must be continuous. Okay. Next, I want to do a couple of examples of some of the things we just talked about. So first of all, given a function, you want to try to sketch the derivative of the function. So let's say our function looks like this. And usually this sort of problem, if you have the general look of the derivative, that's going to be good enough. We don't need to get into real specifics, which is why I didn't even put numbers on my vertical axis. Okay, so the best way to go about this is to first identify the places where the slope is 0, which is going to be here and here. That's at x equals 1/2 and x equals 1.5. Okay, so let me start sketching the derivative. So if this is y equals f of x, this bottom graph is going to be y equals the derivative. Okay, so at 1/2, our slope is 0, and the derivative is the slope of the tangent line, so the derivative is 0. And at x equals 1.5, the slope is 0, so at 1.5, the derivative is 0. Okay. Over here, our slopes are negative. When a function is decreasing or going down as you go to the right, it's a decreasing function, and the derivative must be negative. We don't need to worry about the exact value, it's just some negative number over here. Now, between 1/2 and 1.5, it's going up, so the slopes are positive, so it must be positive, like between here and here, and then negative after 1.5. So I'm going to assume that my derivative does something nice and smooth, and so this would be my graph of the derivative of f of x. Okay. Now, if I wanted to get the exact function, I would need to know this exact function, and then I could use the definition. But the whole point is to just try to sketch the graph of the derivative based on another graph. And the easiest way to do it is first identify the places where the slope is 0, then identify where your slopes are negative, like here and here, and where your slopes are positive. That should be enough to get your rough sketch. Okay. Next example. this is one I've seen in various years at homeworks at UT. So they give us an expression like this: the limit as h approaches 0 of 2 plus h to the fourth minus 16 over h. The goal, however, is not just to evaluate it, but this represents the derivative of some function f of x. They want us to tell what is f of x, and it's the derivative at a certain value of a. So what is the value of a that we're doing the derivative of f at a? Okay, so it's sort of using our definition of our derivative backwards. Okay, so when doing this sort of problem, it's going to help you to just write out the definition of the derivative. Okay, the derivative of f at a is the limit as h approaches 0 of f of a plus h minus f of a all over h. Okay, and then to compare and see where the equations are the same and where they're different, and then try to figure out what f of x is and what a is. Okay, so the limit is the same, h approaching 0. The denominator is the same, both of them are h. Okay, then we have something minus something, and we have something minus something. So I'm going to assume that f of a plus h must be 2 plus h to the fourth, and that f of a must be 16. Okay? Now, because f of a plus h is going to, I start off with some function f of x, and I cram in a plus h. So do I see something that looks like it might be the a plus h, where a is some constant? Well, I have 2 plus h, so maybe a is 2, and a plus h is what I crammed into a function, and this is to the fourth, so it's the function x to the fourth. So putting that together, I'm guessing that f of x is x to the fourth, and that a is 2. Now that would make this part of the equation exactly match. But I also need to check, is f of a actually equal to 16 or not? Well, if a is 2, if you plug in 2 into that function, f of 2 is 2 to the fourth power, which, yes, that is 16. So this is our answer. This represents the derivative of the function f of x equals x to the fourth at a equals 2. Okay. I have one last problem. So we have the sketch of a function, and we are going to evaluate at what values on this function is the function continuous but not differentiable. Okay, so to reiterate, for what values of x is the function continuous but not differentiable? Okay, so first of all, at -1 and 1, it's not continuous, both of these being removable discontinuities. And what I'm trying to look for is places where it is continuous but not differentiable, but those are not continuous. So we can ignore the -1 and the 1. The only other place where something weird is going on is right here at x equals 0. And that's because the slope from the left looks like the slope should be -1. But from the right, it looks like the start of a parabola where your slope would be 0. That is a sharp turn, and that is a place where the function is not differentiable at sharp turns, but it is continuous because the limit and the point are all the same value. So that's the only value, x equals 0, where it is continuous but not differentiable. So here it is continuous but not differentiable. Whereas, just to reiterate, at x equals +1 or -1, it was not continuous, which automatically makes it not differentiable. Okay, so that's going to be it for this video. Hope to see you soon. Have a good day.